Hello, everyone. My name is Jingyu Li. I'm really glad to present our work, PIRANA Faster Multi-Query PIR with constant read codes. This work was completed during my studies at Zhejiang University. I graduated in March and got a master's degree. Private information retrieval is a classic protocol in cryptography. It allows a client to retrieve an element from the server by index while the server doesn't know which element was retrieved. It enables a wide range of privacy-preserving applications, such as private contact discovery, private contact tracing, private navigation, safe browsing, and so on. A lot of solutions have been proposed for this problem, such as Zero PIR, Onion PIR, Spiral, Simple PIR, Constant Weight PIR, and Batch PIR. All of them are based on FHE. Even though its performance has been continuously optimized and improved, it's still not efficient enough to be used in practice. The important challenge is how to minimize the communication cost and computation cost. For easy understanding our work, we need to briefly introduce the two important preliminaries. The first is fully homomorphic encryption. It allows computation on encrypted data without decryption. It supports addition and multiplication of a ciphertext with a plaintext or between two ciphertexts. Particularly, it supports single instruction multiple data. A single multiplication or addition operation can compute n elements in batch, where n is a selectable parameter in FHE, which denotes the polynomial degree. Besides, it supports SMD rotation to change the item position in the ciphertext. Usually, multiplication of two ciphertexts and SMD rotation are both really expensive. In the algorithm design, we need to use those expensive operations less. Another important preliminary is constant weight code. Its code words are binary strings that share the same Hamming weight k. For example, when the length m is 8 and the Hamming weight k is 2, the code words can look like this. We can easily map the original index to a constant weight code by order. A binary constant weight code of length m and the Hamming weight of k. The size is m choose k. If we fix k and n, the code length is the case root of k factorial n. To check equality between an encrypted x and a plain code y, it can use the equality operator. First, we encrypt the x to m ciphertext, and we try to check if x is equal to y or not. For example, if y equal to 1, we can observe the constant weight code of 1, in which only the first bit and the second bit are 1, others are zeros. So when we multiply the first ciphertext with the second ciphertext, and the multiplied result will be 0, which means not equal. Then we set y to 0 to second and do the same thing. Then we multiply the result will be 1. That means the encrypted ciphertext is equal to y. In the original constant weight code PIR, it needs n calls of equality operator to compare the encrypted x with all index, which requires n k-1 ciphertext multiplication. It's really expensive. We want to reduce that. Now, let's begin to introduce our algorithm using a simple demo. At first, we rearrange the database into a matrix of n rows and t columns. Then we use constant weight code to encode the query. For example, if we want to retrieve the second item in the database, then we compute the row index, which is 2, and the column index, which is 1, and we use constant weight code to encode the column index 1, and choose the second row of query vectors to fill this code. Then client uses homomorphic encryption to encrypt the vectors and send the query ciphertext to the server. Server uses multiplication to do t times of equality operators to get the selection vectors, in which only the position of the designed item is 1 and other are zeros. Then multiplies them with the database and add the result together. At the end, server sends back the result to the client. Client decrypts it and gets the designed item. By simply using the SMD features, it can significantly reduce the number of multiplications. It will be more efficient. However, the simple demo only can compute for the item is smaller than the slot size. For the large payload, we need to use rotation to pack more ciphertext to reduce the response communication cost. But if we simply rotate the multiplied result, there may be too many rotation operations, which could become new performance bottleneck. Therefore, we need to optimize this algorithm. We rotate only one step per rotation instead of any steps, which can reduce the number of required allocates and be more fast. We try to rotate the selection vectors with the plaintext database, not only the multiplied ciphertext, which can reduce the total number of rotations. If we rotate the selection vectors alpha minus 1 times, then the total number of rotations can be represented like this formula. When the payload size is large enough, we only rotate the selection vectors with a plaintext database. When the number of elements is large enough, we only rotate the multiplied ciphertext. If in the middle ground case, combine the two methods. Observing the query part, the question is that, can we use other slots to batch more queries? The answer may be no, because multiple design elements may be reset on the same row. But fortunately, the PBC can help us solve this problem. It can encode server's database by PBC and treat each bucket as a row. Then the designed elements are in different buckets, which means in different rows. PBC constructions based on three-way cuckoo hashing, which encodes n elements into M-code words distributed among big buckets with a small failure probability. The more detail about how to implement PBC you can find in PIR. The next question is, if we use multiple rows to batch more queries, can we still use SMD rotate to combine multiple ciphertexts in multi-query PIR? The answer is yes, but the rotation step needs to be changed to B slots instead of 1, and the rotation optimization is also applicable, and we need to change the arrangement of this n bucket. But if the number of buckets itself is close to n, then the result is dense and doesn't require further compression. And we also can directly use multiple slots to encode the same query of one bucket. Then it can reduce the number of rotation. Then let's consider about the extension from multi-query PIR to LPSI. It needs to solve two important problems. First, it needs to support keyword queries, not only index queries. Cuckoo hashing can help it. It can efficiently map the keyword to the index, and then use index PIR is okay. Another problem that needs to be solved is how to protect the server's database. The classic PIR doesn't protect the database. OPRF can be helpful. It can make the database look like random string, and the client only can get the item which it queried. Compared with API-SI, our method can get rid of the expensive polynomial interpolation. It is much faster in the runtime of the setup phase. When you need to update the database frequently, it may be more friendly. Then let's see the experiment result. It can significantly improve the performance of single query PIR based on the constant with code, because it has less MTT transformer operations and less ciphertext multiplications. For multi-query, we try to compare it with the performance of many related works. For 256 byte payloads, it takes only 12.1 seconds to answer 4,096 queries, achieves 812-fold amortization. For 256 queries, PIRANA is 24.8 times faster than Onion PIR and 8.2 faster than Spiral. Compared to the state-of-the-art batch PIR work, our work can perform much better in the answer generation time. It can achieve 40.4 speedup. In some conditions, it can perform better in both communication cost and computation cost. In conclusion, we designed a new PIR with constant with code, PIRANA. It's up to 188.6 times faster than the original CWPIR, and it supports multi-query with minimal extra cost, which performs much better than the SOTA batch PIR. It can be easily extended to solve LPSI problem, which is friendly for frequently updating database. I collect part of the questions and answers in the QA session there. The first is why not generate log2n Galo case to support any steps of rotation? It's okay, but it will be more slower. For example, if we want to rotate 6 steps, actually we need to do 2 key switching operations. If we only use 1 step rotation in the algorithm, each rotation uses exactly only 1 key switching. Another question is that why not use more smaller polynomial degrees such as 2048? A smaller polynomial degree may be efficient, but the noise bucket may be not enough. So the result will be wrong if the noise is not enough. And if you have any questions, you can email to me. The code is publicly available. Thanks for your attention.